Today, we're going straight under the hood of large language models. Look, you already know what these tools can do in the real world, but today we are going to visually map out the exact mechanics of how they actually translate raw data into reasoning. It's pretty fascinating stuff.
Okay, here's our game plan for today. We'll start with number one, what is an LLM? Then, the massive scale of data. Third, how LLMs actually work. And finally, real-world business applications.
So let's jump right into section 1. What exactly is an LLM?
To really understand a large language model, we first need to talk about its parent category, which is called a foundation model. Basically, this is a model pre-trained on huge amounts of unlabeled, self-supervised data. The key takeaway here is that it learns from massive, raw patterns. It is absolutely not being spoon-fed specific, rigid rules by a programmer. Because of that freedom, it produces outputs that are incredibly generalizable and adaptable to tons of different situations.
Now, what sets an LLM apart from a standard foundation model is simply its diet. It isn't learning from images or audio. Its entire universe is made up of text and code. We're talking books, articles, conversational logs, programming logic, the whole shebang. It is basically a highly advanced pattern recognition engine entirely obsessed with human language.
Moving right along to section 2, the massive scale of data.
To really grasp how these models operate, you have to anchor your understanding of the scale we're dealing with. Think about this. Just one single gigabyte of data holds roughly 178 million words of plain text. That's practically a whole library sitting in a tiny folder on your desktop.
But here's the crazy part. LLMs aren't trained on just a few gigabytes. They ingest petabytes of data. And 1 petabyte? Well, that's 1,000,000 gigabytes. So you're taking that 178 million word count and multiplying it by 1,000,000. The model is essentially reading the entire internet to map out the deep underlying patterns of how we communicate. As the model digests this petabyte scale ocean of text, it uses internal values called parameters to keep track of what it's learning. Honestly, the easiest way to think of parameters is like billions of independent little dials. The more dials a model has, the more nuanced and complex its language mapping becomes. To put some hard numbers to this concept, let's look at GPT-3. It was pre-trained on 45 terabytes of data, and it operates using an absolutely astounding 175 billion parameters. It is this massive, intricate matrix of dials being tuned perfectly that allows it to generate such remarkably human-like output.
All right, let's pull back the curtain. In section 3, how LLMs actually work. When you break it down, the mechanics of an LLM really rely on 3 core components working together: the data, the structural architecture, and the training process. The architecture driving models like GPT is a specific type of neural network called a transformer. And this was the real game changer. In the past, computers read text linearly, kind of one word at a time, which meant they quickly lost the context of a long sentence. But the transformer allows the model to map how all the words relate to one another simultaneously. It's like looking at the entire puzzle at once, rather than staring at a single piece, allowing it to understand deep context from the very first word to the last. Then we get to the training, where the core task is literally just predicting the next word in a sequence. Now, at first, an untrained model operates on pure randomness. If you give it the prompt, the sky is, it might just blurt out bug. Obviously, that's completely nonsensical, but it happens because those billions of internal parameter dials haven't been tuned yet. But here is where the magic happens. With each guess, the model compares its output to the actual text it's training on. It registers the error, realizes bug was wrong, and slightly adjusts those billions of dials to close the gap. By iteration 2, it predicts blue. Boom, hit the nail on the head. Now multiply that exact feedback loop by billions of iterations, and you eventually get a model that naturally generates perfectly coherent logic. So, once that massive general prediction engine is fully built, we move to a phase called fine-tuning. This is where we take the general model and train it on a much smaller, highly specific dataset. Think legal documents or maybe specialized medical records. This transforms it from a general conversationalist into a highly accurate, specialized expert. Which brings us nicely to section 4, real-world business applications. Today, businesses are deploying these fine-tuned models across the board. In customer service, they're powering intelligent agents that instantly handle Tier 1 queries, which frees up human staff for the really complex, nuanced issues. In content creation, they're drafting copy, writing emails, and structuring scripts,
And in software development, because they were trained on vast amounts of code, they can actually generate and review entirely new software architectures right on the fly.
We are literally just scratching the surface here. Think about it. What started as a raw architecture awkwardly adjusting parameters to predict the word blue has rapidly evolved into an engine driving global business efficiency. As these models scale up even further, expanding their parameters and digesting even more data, what entirely new paradigms of problem solving are we going to discover next? Thanks so much for joining me on this explainer, and I hope you keep questioning and exploring the incredible technology evolving right around us.